Hello, I'm starting the class of the industrial plant genomics. Today, what I'm gonna do is how to compare you model plant and orphan crop. So orphan crop is usually the industrial crops, usually orphan crop. So definition is that orphan crop are a diverse set of minor crop like tuff and finger millet, yam, root, and tuber that tend to be regionally important but not traded around the world and receive no attention by research network. So, but nowadays, becoming the price of the NGS is cheaper and cheaper, and these orphan crops are also sequenced. So we have draft genome of orphan crops such as rubber tree we analyzed last classes. So what we're gonna do is transferring the knowledge from Arabidopsis to the orphan crop. So how do you do it? So simply we can blast it. So when we so I will show you the information of the Arabidopsis plant EMBL and go to download. Okay, and you can see Arabidopsis thaliana. You can see the Arabidopsis thaliana, and it has GTF and TSV. Maybe okay, maybe I think GFF3 is self-containing the information. So I will download it using IPython notebook. iPlant Jupyter Lab. So what I'm gonna do is comparing the comparative genomics. We usually call it comparative genomics. Transferring knowledge from model plant to what orphan crop. So let's download Arabidopsis thaliana file. The reason why it is downloading to here is that I already have it, which means so I think I already have it, the file. So I will import from PD and data frame PD read CSV. Arabidopsis GFF sep tab and command shop what file not found 부르는 거니. Okay, data frame head. Okay, I don't want to have header, none. Right? Okay, and I will grab the Italiana. We can grab shop and head. Let's see. Okay, it has a lot. It has things a lot. And maybe 20. Minus 20. Mm-mm. Hmm. I think I have to open it up by myself. Rapidopsis. Italiana. 47. I don't know what is the meaning of 47. Okay, it doesn't have headers, so we don't have a header here. So let me just ignore the header. So each gene have certain descriptions. I will retrieve the description by masking gene data frame IM, right? And data frame gene would have like this. And do I have Kang input? Kang? No, there's no Kang. Okay, then I will make 귀찮아. Okay. Anyway. So 8 we gives you name and description. Okay, so name and description it will give you. We will parse it. We will parse this information by use 0. So how do you do it? I will split by shop. No, semicolon. And I will split those. By equal. You will see the result like this. Then I will make it into dictionary. Okay, so you will see now we have dictionary that contain name and biotype and description and so on. So what we're gonna do is constructing the dictionary. Exactly like that. But it contain list. So name and biotype and description. So we don't need biotype, right? So we don't need biotype. So I will just have description. That's it. Description. Okay. So we will iterate. So we select just the first one, right? So we will iterate. Each in we will put each there. Okay, we will put each there. So this should be indented. So each dictionary we will define, and dictionary ID append each ID. Dictionary name append each DA and name. Dictionary description append each dic and description. Okay, so why we have the error? Then let's print each. So mostly it has name, but sometimes it do not have name at all. Then except key error, if there is no name in the string, we will append none. So let's okay, description itself also sometimes not there. Description 아이고 append none. Okay, so data frame tick. So we have the list of, but I don't like this gene. Then replace gene. Now we have a table. We have the description. Data frame. Annotation. Arabidopsis. Now we have it. Now we have the annotation. So let's save it to picker. So this is coming from this file. So I will name it like annotation pk. Good. So we have the annotation. So this is a kind of starting point to give you. So so whenever you want transferring the knowledge, at the first you have to have the knowledge, right? So this is the knowledge. So we now have knowledge to transfer. I will give you one more option to retrieving this knowledge from this site. So what we have done is downloading this GTF file, GFF3 file, and we parsed by Python, and now we have this table. So now we have this table, and it contains ID and name and description. But this is kind of the coding intensive. It's not intensive, but sometimes some people feeling it is very intensive. So then you can use Biomat. So Biomat. And from the Biomat, you can choose database, ensemble, plant, gene 47. So version 47, gene. So we are talking about genes. So let's click on the gene. Data set should be coming from Arabidopsis thaliana. Let's wait for a while. Then it will give you attribute. So selected attribute is gene stable ID, transcript stable ID, and what we have. So I don't like transcript stable ID. I don't need. And external, then you can add geo accession term, geo term name, and some ID, some reactome ID, tear ID, and some description. Okay, gene description is there. And what? Maybe you can select more if you are interested in each element. And also you can add this domain information. So select everything you want. So maybe I will add more or more interpro ID and interpro description. Then click on result. So this is really good because you want you can add everything that you want, because in this case this only containing the description, the maybe the source is UniProt. So UniProt description is only contained. However, here you can add interpro description, and this description that is coming from the UniProt, and you can add geoterm also. So because you add geoterm, so it gives you redundant information. So I will remove geoterm. So I don't like redundancy. So this gives you about this also gives you redundancy. So I don't like. Okay, so one gene have many interpro ID. This would not be good. So reactome ID removed, interpro ID removed, interpro short description. Let me have it. Okay, this also shows redundancy. Let me remove it. Then what is more? What is more we have? So shortened gene synonym, gene name. Let's have it. Okay. So now we have a certain annotation table. So let's download it. Go. No, I will have it. CSV. Go. Then it will download. And move it here. Then you have marked export to here. And rename it EMBL Arabidopsis Biomart export. So PD read CSV EMBL. Then you have it. EMBL, no, Biomart Bidopsis. See? So this is the way we are doing. And you can download the target target sequence laboratory. So what was the scientific name of laboratory? I forgot. Laboratory. So this was the our I thought we have the protein sequences, no? So heavier branches. Let me check if ensemble have it. Heavier. So there is no heavier in ensemble plant. Then we have to go to here. So okay, so we have protein here. We have protein and we can download it. So we have protein download. Okay. And we have Arabidopsis protein. Arabidopsis protein here, right? So here. And protein or good. Then let me use terminal. So we have, so I want to make a new folder, blast. So ln makes a symbolic link of, no, so I will copy it. So gc protein here. Arabidopsis thaliana pep. So we have two files simplified, and I will make blast. Okay, I don't have blast yet, so let me install blast using conda. Blast. Conda install bioconda blast. So after install Blast software, then you will now you will have make Blast DB. So you can run this make Blast DB. So we will make a Blast DB using in. Okay. So we'll make the Arabidopsis DB. So DB type. So I don't know if it will support the no, it will not support the gunzip compression. So we will uncompress the gunzip. So now you don't have the .gg. You don't have the .gg, which means this is uncompressed already. So you will see the size is significantly increased. Okay, so remove gunzip and run. Then it takes bit while to construct the database. Actually, it is not database. Actually, it is as far as I know, this is index. So based on this index, the Blast can align the sequences onto the Arabidopsis. Okay. So Blast P. Blast P is protein blast, and the query will be this one, and the DB is this one, right? And output format. Okay, let me just leave output format as default, and the out will be test. I will just put it test, and number of alignments 1. So I want to have only top hit, just first alignment, best alignment, and the E by U usually 1E minus 5 or 10. So I will put it 1E minus 5. Okay, so and number of threads 2. So there is not a, okay. This should also unzipped. Let's run it without unzip. Then it will take for a while. So let's wait for a while. So after running the blast analysis, you will get the result, the test, and then you can see the matching. So the first one is a query. So query is coming from what? Coming from GCF file. So GCF file looks like in this way, and it has ID and description. It has ID and description, and then this ID is matched to this gene. So I wonder if, so I think this is quite too long, right? So this is very long to interpret the result. So we usually do is that we put output format 7. So out FMT 7 out, and so number of alignments is 1, and okay, run. So it takes time, so I will stop here, and you can see the result in this way. So then this query was matched to this only one, and this query matched to this only one. So then we can directly think that, okay, if you have any knowledge from these genes, then you can transfer to these genes. So this is a simplified analysis using BLAST. So this is how you're doing. So I will put this command to the here. Then you guys can download the file and try, or yes, but it will take a lot of time to get the final result. And the other approach is that using eggnog database phylogenetics, then you can see the eggnog database. However, sometimes it will not contain any, species, like rubber trees, because rubber tree is orphan crop, so maybe it will not have the information of the rubber tree. So if you search on Arabidopsis thaliana, then it will give you back very large cluster. So let me go back to the BLAST result. So this direct match may not be representative, because sometimes this one is not so close enough. For example, this value is similarity. So in the case of this gene has 77% similarity to this gene. However, in this case, it gives you back this number, 49% of similarity to this gene, which means maybe this gene is not so representative to this gene. So if you considering the clustering with neighbor species, then these genes may not be belong to this cluster. Okay. So we have to consider this clustering situation. So eggnog is a database that every reported species was clustered. The protein from every species that has been constructed was clustered to see the Ursula group. So if I search this gene, then it will give us the annotation, signal transduction mechanism, and the cluster ID is assigned. So code 0589 is the cluster ID. Then what kind of gene is participated in this cluster we can see easily. So then I don't think it will have the rubber tree. I don't think rubber tree, heavy up. I don't think they will have a heavy up. No. Right? So it will not have a heavy up, but if you are interested in the orthologous relationship, between distinct species, then you can use this eggnog database. So in this case, Piscomytella paten is a green plant, but it is not land plant. It is moss. Moss has direct ortholog to this gene. So we can determine, okay, we can compare that two genes without any doubt. But if you use just BLAST, then it will be very hard to determine, okay, these two genes has similarity, but the other genes has very low similarity, such as 73 between these two genes. Then yeah, it is a bit hard to determine true ortholog relationship or not. But the problem is we don't have any information of laboratory in eggnog, so we have to retrieve the ortholog relationship with other methodology. So the other methodology is also MCR. So also MCR is the other methodology that we can extract the orthologous relationship. It rely on the BLAST. So it rely on BLAST. Actually, I don't know exactly how orthologous also MCR is working, but one thing that I know is it use the numbers of this. So it use these numbers as a feature of these two relationship. Then it will cluster, right? So it will cluster. Then if the clustering is done, then it will assign the cluster ID like eggnog. So eggnog has cluster ID like this. So we can manually, and it's not manually, but in using local computer, we can assign cluster ID. But it will not be that correct as eggnog, because we usually do maximum 5 or 6 species for the clustering. So it may be correct. It may be correct, but it's sometimes it may be not correct comparing to the eggnog, because larger data gives you more correct view, I would say. So also MCR is the other way. So also MCR is very tricky software. So for me also, it's always give me headache. But if it is necessary, then we have to do it. So maybe if you are asking, then I will show you how to use also MCR. And the other way is using synteny. So synteny is that collinearity. So I told you that. So in this case, the pineapple and Arabidopsis sharing the gene order. So the gene order, so A and B and C and D genes are conserved in pineapple also, A and B and C and D, or A and B and D and C, for example. But the order is slightly different, but the order is well conserved within specified genomic region. So as far as we know, the plant do not use operon. So prokaryote use operon system. So what is operon? Operon is the functional unit. So let me read it. In genetics, operon is a functional unit of DNA containing a cluster of gene. So cluster of gene will be conserved because of the function, right? So this cluster has been formed for certain function. So that is operon. But in plant, there is no, report, as far as I know, operon. So, so there is some kind of report, rise of operon-like gene cluster in plant. But the reason why they report is that the operon is very rare in a eukaryote. So I think this is the synteny is kind of indirect evidence of this operon-like cluster. So how can we calculate this situation? So synteny, observing synteny is based on the gene collinearity. So I mean the position within a certain genomic region and similarity. So we have to use BLAST and calculation of the position. There is a software for this, very old software but very effective, MC-Scan X. So MC-Scan X is developed by this group, and we can install MC-Scan X very easily. But let me check if Conda has it. MC-Scan. Okay. So anyway, so this guy is the developer of the MC-Scan, as far as I know, maybe. But the Python version is quite complicated. Yes, we have to use this MC-Scan X for our analysis. So let's download it. 링크 주소 복사. Okay, let's download the MC-Scan X. Get. Okay, this is downloaded, unzip, MC-Scan X, then it will give you back. It will give you back this these files. So as far as I know, you make so apt install. If you type on there and make, then it will compute okay. I have things that we need when you install everything for Ubuntu. So Linux. So this one you have to build everything. That is essential. Yes. So Linux is really good environment for the analysis and developing. However, you have to set by yourself everything when you encounter certain problem. That is only one drawback using Linux environment. However, sometimes it feel like really big overcoming the drawback. But ask me if you have any trouble with Linux, then ask me. Then I will help you how to overcoming the problem. So this is what is that? What is that? CHDIR was not declared in this scope. Maybe we will have very hard time with this problem. So then add include unlisted H as for. Oh my god. Okay, so where is it? Where is it? That was warning, and this was makefile. Makefile. No. So there was makefile, but MSACCVI, and I will include that one and make. Let me see what will happen. Sometimes this kind of compiling, this we are calling this step as compiling. It's really hard because it always gives us this weird error. But usually it is no, it is about you don't have a declaration. Okay. So get opt. You don't have when you have get off not declared, then you have to declare. But I do not know how to declare get opt. So I need to search everywhere. Everywhere. So what is the fix? Get opt. Okay, so I will include this one. I will include this one to dissect alignment to CC. Get opt. Make what? Make clean. Make what? I want to make it again. I forgot how to G plus make clean. Make again. How do I make again? Wow. Anyway, make install. No rule install, only make is there. MC scan X is up to date. Then how do I? Then I will remove MC scan X and H source. Make. So compiling result in that executable file. So After getting the MC scan X executable, it found get opt. What I have done was multiple alignment, but now it give us problem in here, tandem array. So I will give him get opt again. I want to copy it. So this is a bit shitty, but it's okay so far. I think you will get the same errors. So I'm showing this, the procedure how to fix the errors. Okay, so again, what is the error? Java C command not found. So it is required for the downstream analysis. Java C is not found. So this is about Java C. I have to install Java C, I think. Java C. Ubuntu. Okay, apt-get install default JDK is recommended to solve this problem. Easy. Just paste it and give him sudo. 420 megabyte is required. So maybe if you following my class diligently, then you will figure out that bioinformatics is not so, how say, easy. If it is well set up, then it will be extremely easy. But if it is not set up, then it will be a hell. You have to go through the hell to set it up into easy pace. Then your juniors will come to the easy and comfortable environment because of you. But he will not recognize your effort to get through the hell pace to heaven pace. This is the way of setting up guys doing. So I think this is really good to show you how to fix the errors and speak useless commands while installing the softwares. So what I'm thinking is really great for the computer is that they provide everything in free. So everything is free. Hold on. What is the problem? Okay, nothing. So I will remove the executable again and make again. Make Warning is okay. Warning is no problem. Error is problem. Of course, without, with that errors, maybe you can run the executable easy. But I recommend you to solve every error in your environment. So because of that, so everything is done. So no error. So we have the executable MC scan X. Good, right? So MC scan X can be done with this data. This data is, let me see it. So this is the example of the blast. You can see this blast. So Arabidopsis and no, tail. So this must be the grape, I think. So grape and Arabidopsis blast result is inside of this file. So let me check. Cat grab GSB. Okay, so you can see. So it also have the blast result from AT to GSB. GSB is the vinifera, I think. Vinifera is the grape. So self-blast of Arabidopsis and self-blast of vinifera, and blast from the vinifera to Arabidopsis, and blast result from Arabidopsis to vinifera is included in this blast file, and the GFF file of these two is included. But this is not typical GFF file. It is shortened, summarized GFF file. First one is chromosome or scaffold, and second one is gene name, and third one is the starting point of the gene and end point of the gene. So 4 columns is contained in this GFF file. So every genes of the Arabidopsis and vinifera is included in this file. So let me learn how to. This is really easy. MC scan X, and you just add these 2 words. Okay, then it will check if there is dot blast or dot GFF. Run. So it will gives you the result. So the first result is AT and VV vinifera and collinearity, and the collinearity is very well calculated. Okay, so we don't need the within collinearity. What you can see here, Arabidopsis itself has collinearity within the chromosome. You can see the first chromosome. Within first chromosome, you can see the collinearity. So this is the genes. The first gene and second gene has similarity, and this gene has similarity, but these in vertical way, these genes are located similar region. So you can see these numbers is consecutive. these genes are consecutive, right? So this number is synteny ID. Okay, so we can think that this cluster, synteny cluster, may have a certain functional meaning. We do not know. Some kind of context we do not know, but there is a context why this block is that conserved. After you search B, then you will find, okay, Arabidopsis cluster of these also conserved in Vinipera grape. In grape genome, these gene order are very well conserved. Interesting, right? So, and if you go to the scan X and result and data and HTML, then you will see the result in visual way. So, okay, this, oh my, it is really slow. Okay, I think this is so big. I think I need to close this file. Close. 꺼져. 이런. So it exceeds the memory allowance of my computer. So I will close it. So yes, and I will I will go to my I will go to where was it? The PC and C drive and Ubuntu and iPlant and what? Blast, MCScanX, data, HTML, and you can see this is over 2 mega, so we can observe in this way. So if you zoom out, zoom out이 안 되냐? It is okay. So this is order of the genes that I think from Arabidopsis chromosome 1. So it takes a lot of time. So because it render in this way. But I think you are understanding what I'm saying. So how this gene order is conserved. So this is another evidence that these two genes are also logos or paralogous, not just showing similarity. So this big block is going together as a, I would say, evolutionary conservation. Okay, so this is why we can call these two is real orthology or paralogy. Okay, and I was thinking that there was what was that? Downstream analysis that will give you some kind of plotter. So I don't know if I can learn this one or let me check the downstream analysis. Dot plotter, no. No, no, no. Bar plotter. Let me see. Okay, so we can plot the result in this way. So how do I do it? Okay. So this is dual plotter. So Java dual percentage plotter. No, 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 no. Oh yeah, yeah. So let's just add AT and VV, right? And AT and VV and control. What is the CTL? I don't know. Kind of configuration. Let me see it. Dual plotter has CTL. Okay, CTL gives you some kind of expressions. Then I will select okay 81, 82, and hold on. I will okay some kind of error. I will check the data and AT and BB collinearity and no no yes B. So these genes are coming from what? BB. No. No. AT VV GFF. Grab. Okay, BB1. BB1 is there. BB1 is there. So and I will no. Yes. I will grab this one. Everything was what? Okay, just BB1. BB1. 81 and BB1. Let's see it. Let's see it. Just let's see it. Downstream analysis and run the file. Control dual synthetic plotting. I will say AT and VV dot. Okay, it is done. It is done. Then I will open it. The result. Okay. So it gives the lines between 81 and BB1. So this showing that these blocks in Arabidopsis are conserved in BB1. So BB1, this region of BB1 has conserved synteny block between Arabidopsis and Vinipera. Okay, so we can explain our result to the reader. So our observation strongly suggests that these genes are also logos along with the evolutionary path, right? So what we're usually doing is that put if you have information on this region, genomic region, then we can translate the information to here. If you have a certain information here on these genes, then we can translate to this here, this region. Okay, so sometimes if you have QTL, then QTL you have here, then we can transfer the QTL here. And if you have a strong QTL here, then these large region may be responsible for that QTL also. This is how you transfer the synteny information to other chromosome. Okay, so I will stop I will stop the lecture here, and next week I will learn our data, the Arabidopsis and rubber tree, to make this kind of synteny plot. We will make by ourselves this synteny plot, not using this JavaScript. I mean, this is not JavaScript, this is Java. I will not use this Java code. I will use Python code to visualize the data. Thank you for watching.